Many of the measurements that we're going to want to do with the 82 scope involve looking at the noise picked up on a victim line created by an aggressor. And so we're going to have a large signal that we're looking at as the aggressor. That's what we're going to use to trigger the scope. And we're going to want to measure a small signal on channel 2 that is the noise on the victim. We've seen that there are a couple of sources of artifacts, other sources of noise that we can see in the scope that aren't just victim noise. We saw the impact of 60 Hertz noise and RF noise. Now we're going to look at another source of artifact that can interfere with a measurement of a low-level signal on the victim line, that is the noise, from the aggressor line on channel 1. And that's related to the inherent crosstalk between channel 1 and channel 2 inside the scope itself, or from the cables that go from the scope to the device under test. And that's what we're going to look at in this video. We're going to use as our aggressor a square wave from an Arduino pin. This is roughly a 5-volt signal. That's going to be going into channel 1 of the scope. And we'll look at that signal. We'll use the signal coming in from channel 1 to trigger the scope, and we'll look at the noise on channel 2 when nothing's connected. How can there possibly be any signal on channel 2 if there's no connection to the outside world? We're going to see that there is still some crosstalk inside the scope itself, on that printed circuit board of that scope, between channel 1 and channel 2, and we'll see it very clearly when we have a large signal on channel 1, and we'll distinguish how much of that noise is capacitive coupling versus inductive coupling by changing the impedance of channel 2. If we have an open on channel 2, then we're sensitive to capacitive coupling. If we have a short on channel 2, we're sensitive to inductive coupling. And we'll see the impact of that coupling on the noise we pick up on channel 2. This is going to tell us about how much crosstalk is there between the signal on channel 1 and the signal we're picking up on channel 2. We want to know what this is so we don't confuse noise that we see in the scope measurement from the source. If it's coupling within the scope, it's not related to the impact the aggressor has on the victim line. It's an artifact of the measurement. And because we're going to be looking at really low levels of voltage pickup on channel 2 due to this internal coupling, I'm going to show you a trick we can use to pull that synchronous noise, synchronous with the aggressor signal on channel 1, on channel 2. I'm going to show you the trick to pick up the noise that is synchronous with the aggressor when there's a lot of other random noise involved. And we're going to be averaging successive sweeps of the scope. This is a really powerful trick that we're going to use over and over again when we want to measure low levels of switching noise or low levels of noise that is synchronous to some source. And that's different from random noise, which will average out with the square root of number averages. The noise that's actually synchronous with the trigger will always be the same, and we'll see the random noise level decrease for that small level signal to appear above the noise. Let's take a look at the setup in the lab. Here's our really simple setup. We have the Arduino. We're running a modified version of Blink, so it's on for a millisecond, off for a millisecond, and we're looking at the signal on pin 13 over here. Now I've switched the connector from the 82 scope to the device under test because I want to eliminate as many sources of coupling as I can. In this case, we just have 2 wires that are still attached to the ribbon cable. And why are we doing that? One is connected to the 1 plus and the other one's connected to the 1 minus channel. Because it's a differential measurement, but I have the minus channel connected to ground, I'm looking at a single-ended voltage, and in order to establish the ground on the board of the Arduino to be the same voltage as the ground of the 82 scope, I'm using the USB connection. So the ground is connected to the USB hub, and likewise the ground on the USB connector here is connected to the USB hub, and so those grounds are at the same voltage, and that means that I don't have that common signal noise that's introduced in the artifact. Always be careful to avoid that problem. So I'm really measuring the single-ended voltage between pin 13 and ground. And I've got the Arduino running the code, so I should see about millisecond on, millisecond off. It's about 500 hertz signal, 0 to 5 volts. That's going to be the aggressor. Let's take a quick look at that. And sure enough, here's the scope setup. I'm triggering on, let's see, I'm doing auto. I got channel 1 coming in. That's my source. I'm triggering the rising edge, and here's my trigger level. Nice, beautiful, wonderful looking signal. Exactly what I expect to see. Here's my 5-volt signal. This is the aggressor. You'll notice that channel 2 over here, there's absolutely nothing plugged into it. And so we shouldn't see any voltage at all when we look at channel 2. It's an open circuit, but there are no leads. There are, of course, traces on the board until it gets to that amplifier where it's turned into a digital signal. That's on the circuit board inside the 82. But we shouldn't see any noise on channel 2. Let's take a look and see what's on channel 2. So we're going to turn on channel 2. It's 0 volts, but you can see the barest hint of, uh-oh, there is something going on synchronous with the aggressor signal on channel 1. Let's zoom in so we can see that a little bit more. Here's 50 millivolts, and now we're beginning to see that signature. Here's 20 millivolts. Hey, let's see a little bit more, 10 millivolts. And so we see the peak to peak, let's see, it's 10, 20, maybe 30 millivolts plus 30 millivolts minus. So that's 60 millivolts plus and minus. And the signal coming out of the Arduino is 5 volts. And so we see that noise is roughly about 50 millivolts out of 5 volts, about 1%. It's not a lot, but it is very clear and present. Where is that noise coming from? I mean, there's absolutely nothing connected to channel 2. It's coming from, because it is a high impedance input, that tells us it's going to be capacitively coupled to the from the aggressor. It's coming from the capacitance on the circuit board between the channel 1 traces on the board and channel 2 traces on the board before they get into the amplifier. It might also be happening inside the amplifier itself. There may be some crosstalk there. Can't separate it from this measurement, but it's all about the intrinsic coupling in the 82. This voltage noise that we're seeing here is going to be present whenever we have a high impedance on channel 2 and we're looking at an aggressor signal on channel 1. There's fundamentally nothing we can do about that. We just have to be aware of it. And so that says when we look at high impedance measurements on channel 2 and we have a high aggressor signal on channel 1, watch out, because we could have about 1% capacitive coupled noise on channel 2. That's one of the limitations of the 82 scope. Anything we do to the interconnects, anything we do to increase the coupling between the wires of channel 2 and channel 1 is only going to add to that capacitive coupling. That's capacitive coupling. Now let's look at the inductive coupling. And the way we do that is we're going to add another pair of wires to channel 2 and we're going to short the ends. So the input will be shorted and we'll try to keep that loop far away from the aggressor loop. Of course, when we short the ends of the inputs to channel 2, we're going to be sensitive to magnetic field coupling. There's very little magnetic field coupling on the board itself or in the amplifier. It's all going to be due to the cables that we see on the outside. And again, it's all about how much coupling there is between the loop of the aggressor that's generating the magnetic fields and the loop of the victim line that's going to be sensitive to the pickup of those changing magnetic fields. So let's plug in our other loop and look to see how much inductive coupling there is channel to channel. So we have another loop in channel 2. Again, I've kept them on the ribbon cable, so I have them as tightly coupled as I can given the discrete nature of the wires. I'm going to keep the channel 2, the victim line, I'm going to keep that far away. We know that there will be capacitive coupling, and we'll see some pickup on channel 2, but I want to look at the inductive coupling. So I'm going to short these two leads together. So I'm just using the solderless breadboard to make the short, and now I can keep those wires far apart. So I'm going to dramatically reduce the inductive coupling between the aggressor loop and the victim loop, and now we'll look at the crosstalk, the magnetic field crosstalk, the inductive crosstalk inside the 82 scope. Well, you see a dramatic reduction in the capacitive coupling. If I open up the leads, there's the capacitive coupling. there's the capacitive coupling is gone because I've pushed that pole frequency to much higher frequency and I've filtered out the capacitive coupling. Now I'm sensitive to the magnetic field coupling. And now let's zoom in and take a look at how much magnetic field coupling there is. So we're at 10 millivolts a division. Here is 1 millivolt a division. And you can see that, gosh, there's a lot of random high frequency noise. This is the lower frequency. And remember, if it's magnetic field coupling, what is the only thing that changes the magnetic fields inside this loop? It's changing magnetic fields from this loop. And what is the only thing that causes changing magnetic fields? It's changing current. And that's what's going to happen on this edge. And so we want to zoom in on the edge to look at the very short time noise when I have a DI/dt. Now there shouldn't be a whole lot of DI/dt in this loop. There'll be a little bit because of the current change, the current charging up the capacitance of the two wires and the input capacitance of the scope. So there will be a little bit of transient current going back and forth, but we wouldn't expect a lot of transient current. Let's take a look at how much noise we see when we zoom in on the edge. So here's 20 microseconds a division. Here's 1 microsecond. Hey look, we can just barely see the hint of some very fast noise happening right at that edge. That's 1 microsecond. Let's go to 200 nanoseconds a division, and now we begin to see maybe there is something going on here. Unfortunately, there's all this random noise as well. We want to see the noise that's synchronous with the edge switching. And so here's the trick we're going to do. Most of this noise is random. If we average this buffer and take the next one and the next one, we're always triggering on channel 1. All the random noise is going to average away with the square root of the number of averages. Any real signal on channel 2 that's always there will stay there, but we'll average out all the random noise and drop that. And so the noise level will drop, the signal level will stay at the same level. And the way we average multiple sweeps of the scope buffer is the secret location under the time base. You'll notice there's a little arrow. Push that arrow and we pull down and we get a whole new menu available to us. And we're going to select average. This is going to be the number of sweeps, successive sweeps that we average, each one synchronously triggered on the aggressor. And so right now there's no averages. Let's make it 50 averages. And so the noise level is going to drop by the square root of 50, which is roughly around 7. The signal will stay the same. And you can see, oh my gosh, there's a tiny little bit of noise that's kind of sometimes there. It's not real stable because, of course, because we've got our victim line far away. If we were to, so that says inside the scope, not a lot of inductive coupling. Now there's not a lot of current flowing through there, but there's a little bit during this dVdt period of time over here at the edge. We are really at the limit to what this poor little scope can do. We're at a millivolt per division, even with the averaging. If we were to bring that victim line closer to the aggressor line, then we'll get coupling between the wires, not in the scope, but in the wires, and we might see an increase over here. So let's bring that loop closer together. And sure enough, there's a little bit increase. There's a little bit of current dI/dt in the aggressor loop. There's a little bit of magnetic field coming out. Even though these two wires are close together, there's still a loop. Likewise, there's a loop here, and we're seeing the noise induced in this shorting loop on channel 2 from the dI/dt in channel 1. And if I get them really close and hold them in close proximity, you can see, hey, we get even more inductively coupled noise. If I pull them farther apart, there's less crosstalk between those two channels. Even if we have the two wires connected together still on the ribbon cable, so there's a small minimum amount of loop, and we bring the two loops close together, we're still going to have inductively coupled noise. That is a fundamental limit of the cables that we use from the scope to the device under test. And this is one of the most important reasons why, if we care about low-level noise and crosstalk, we don't want to use discrete wires between the 82 scope and the device under test. And we also want to always be careful of minimizing the loop area of the probe between the signal and the return, and keep those two loops far away from each other so we don't have this inadvertent channel-to-channel crosstalk in the measurement system. This is an important artifact that we want to avoid. And it also says whenever we're measuring low-level signals, we always want to be careful of how much of that noise that we're seeing, the synchronous noise that we're seeing, how much of that is due to an artifact of the measurement system versus an actual measurement on the device under test. This is going to be an important consistency test that we're always going to want to think about doing whenever we look at low-level synchronous noise.